On the topic of random variable, suppose we have a sample space. And we denote it by S. A random variable on S is any function or any rule that assigns some values to the elements in the domain that here we denote by S. So a quick note for you. We represent random variables as functions by capital letters like X, Y, and so on. When it comes to random variables, we either have discrete random variable or continuous random variable. So another note for you. Random variables are categorized as discrete random variables and continuous random variables. We're going to talk about each one of them and go over some examples. Our next definition is the cumulative distribution function. A definition for you, what is a probability distribution? And then we're going to introduce the cumulative distribution. So let X be a discrete, random variable. When we're talking about discrete random variable, it means that it is countable. The probability distribution for random variable X is defined as follows. It's basically the probability f of X is equal to the probability that random variable X is equal to X. So let me change this color to highlight this, that random variable X takes on a value like X. Remember that the probability distribution for a discrete random variable is positive, or at worst case scenario is 0. And if you add all of those probability distributions, is equal to 100%. F of X is always more than equal to 0, and the sum of all probabilities adds up to 100% or equal to 1. Basically, we represent it this way. We say that, hey, this summation of all of these probabilities, f of X, as X belongs to the domain, must be equal to 100%, or, as we mentioned, just 1. So these are important properties for a discrete probability distribution, or probability distribution for a random variable, which is discrete. As you guessed, when we are working with continuous random variable, this summation notation becomes the integral. Example for you. Let's check to see if, for example, a function can serve as a probability distribution or not. Example. Check if the following can be used as a probability distribution. For example, suppose we have function f of x, which is given to us as x minus 2 divided by 3, and x is equal to 1, 2, 3, and 4. Take a look. Remember that we have two conditions to check. First of all, the function must be positive, or in the worst case scenario, must be equal to 0. And then the summation of all of those for each of these x values must be equals to 1. So let us begin. We need to check the above conditions. First of all, f of x must be more than or equal to 0, and also the summation of f of x for every x in domain D, for example, must be equal to 100% or 1. So let us start by x equals to 1. When x is equal to 1, f of 1 is equal to 1 minus 2 divided by 3, which is negative a third. Okay, it means that we have issue with this condition. This is negative. So it means that the function cannot be used as a probability distribution. You might say, hey, what if I just change the values from 1 to 2, 3, and 4? So let's see. Now suppose we consider f of x to be the same function x minus 2 divided by 3, and x is 2, 3, and 4. These are discrete values. You can basically count them. These are all countable, so they are discrete. No doubt there. So let us begin. We need to check two conditions. When x is equal to 1, when x is equal to 2, then f of 2 is 2 minus 2 divided by 3, or 0 divided by 3, or 0. So we don't have any issue here. What if x is equal to 3? When x is equal to 3, f of 3 is equal to basically 3 minus 2 divided by 3, or a third. So this is positive as well. What if x is equal to 4? Okay, f of 4 is equal to 4 minus 2 divided by 3, or 2/3. Again, this is positive. So basically, the very first condition is met here. So f of x is positive or 0 in the worst case scenario for all values in the domain. So what's next? Now we need to check if the summation of these y values or output values for every x in the domain is equal to 100% or 1. So let's begin. We need to add 0 to a third to 2/3. So let's check this. 0, which is f of 2, plus f of 3, which is a third, plus f of 4, which is 2/3. Basically, you can see that it is 3 divided by 3, or 1 or 100%. So all conditions are met, and we found a function that can serve as probability distribution. Let's take a look at another example. Let us make it more interesting for you. Consider the function g of x equals to x squared divided by 4. X can take on values like 0, 1, 2, 3, and 4. What about this case? So it's not difficult to see that when we plug in values for x, when x is equal to 0, g of 0 is 0. So we're good. If x is equal to 1, g of 1 is also positive. When x is equal to 2, g of 2 is equal to 4 divided by 4, or just 1, which is okay. When x is equal to 3, g of 3 is equal to 9 over 4. Again, it's positive. And when it's equal to 4, g of 4 is equal to 16 divided by 4, or 4, which is positive again. So the very first condition is met. This condition, just going to copy this guy down, here for you is met. Now we need to check to see if the summation of all of these is basically equals to 100% or 1 as well. Then we can for sure say that it is a distribution, probability distribution or not. But take a look. If we add all of these together, when x is equal to 0, we have a 0 plus. When x is equal to 1, we have a 4. When x is equal to 2, we have 1. When x is equal to 3, we have 9 over 4. And finally, when x is equal to 4, we get 4 back. If you add all of these together, this is equal to, here you have 10 divided by 4, or 5 over 2 plus 5, which is obviously, it is not equal to 1 or 100%. So since this condition, the second condition, is not met, the function doesn't serve or cannot be used as a probability distribution. So in this example, since the summation of g of x, x belongs to D, is not equal to 1, so it means that g of x cannot be used as a probability distribution.